The next topic that we are going to learn in this course is about an equivalence relation representing a regular language. So, before we see that equivalence relation representation for a regular language, we need to collect some basic information about binary relations, in particular about equivalence relations, because in the next class we are going to learn about a special type of equivalence relations called Myhill-Nerod relations representing regular languages. So, before that we need to recollect the basic information from equivalence relations, and that is what we are going to do today. So, we are going to collect some information about equivalence relation, and before that see what is a relation. We can try to understand what a relation is by an example relation defined on a set of persons or characters. This is a set of 12 characters or persons, famous characters or persons: Romeo and Juliet, Bill Gates and Melinda, Antony and Cleopatra, Harry, Ginny. All these are either famous characters or famous persons. Now look at the spouse relation on this set. Here a directed arrow, it's actually a both way arrow, represents that in this direction it represents that Romeo is related to Juliet, or Romeo is the spouse for Juliet. In the other direction it says that Juliet is the spouse for Romeo. Okay, it's a nice relation, and mathematically you can represent it as a set of pairs. Romeo Juliet is a pair because they are related, and in fact we need to have two pairs, Romeo Juliet and Juliet Romeo, but we are not, and that is exactly what we need, but we are not explicitly representing them as two different pairs because they are the same pairs or couples. So, this is an example. Another example on this set of 4 numbers, let us see the less than relation, which is the usual less than on natural numbers. You can see that 1 is less than 2, so they are related. 1 is less than 3, 1 is less than 4. If you look at all the elements to which 2 is related, 2 is related to 3 because 2 is less than 3. Similarly, 2 is related to 4, and also 3 is less than 4, and all the pairs are listed over here. So, that is again a binary relation. Now, we can formally define what a relation is. Let A and B be 2 sets, then their Cartesian product is represented as A cross B, and it is defined as the set of all pairs xy such that x is taken from the set A and y is taken from the set B. So, this is called the Cartesian product. Example, given A and B as these sets, then the Cartesian product is this, the set of all possible pairs, and the order in which you write it is not going to affect your Cartesian product. It is just a set of pairs, not an ordered set of. And you can generalize and say that if there are m number of elements in the set A and n number of elements in the set B, there are going to be m into n number of elements in the set A cross B, which is the Cartesian product. Now you can define a relation as any subset of A cross B, a binary relation, that is between two sets. A relation from A to B is an arbitrary subset of the Cartesian product. For example, here there are 6 pairs in the Cartesian product. So there can be 64, which is 2 to the power 6 different relations on from A to B. Examples: R1 is a relation because it is a subset. R2 is again our relation because it is again a subset, just one element. Interestingly, R3, which is null set, is also a relation. Why? Because by definition any subset is a relation. Now the question is, why we need to have an empty relation? Yes, it is meaningful. In some cases we need to have an empty relation. For example, suppose you are given with a set of persons, maybe the set of students in your class, and suppose nobody is married, then what is the spouse relation you are getting? It is empty because no pairs are there. So empty set is a meaningful relation depending on what you are representing. And I hope the definition of relation is clear. And now we can see some special types of relations. First is reflexive relation. I am giving you an example. The relation is given which is in fact the less than or equal to relation on the set 1, 2, 3, 4. Here you can verify that every element is related to itself. There is a self loop in the directed graph representation. If every element is related to itself, then the relation is called reflexive. It does not matter whether the other pairs are there or not. It may be there or may not be there. If you just take only these 4 pairs, then that also is a reflexive relation, right? This is how you formally define it. You can look at some examples, some more examples. Here is R1, which is represented over here. You can see that it is not a reflexive relation because 2 is not related to 2. That pair is not there. I am giving you another one. Here you can easily see that it is reflexive because the self loops are there at every element. So it is reflexive. I hope what are reflexive relations is okay. Moving on to symmetric relation. If you take the spouse relation, you can see that it is symmetric, and by definition a relation R is said to be symmetric if whenever A is related to B, then B must be related to A, and that is of course true for a spouse relation. If Romeo is related to Juliet by spouse, then Juliet must be related to Romeo by spouse relation. You will not have the situation where Romeo is the spouse of Juliet, but Juliet is having some other spouse. That is not the case. So this is an example, and these kinds of relation where whenever A is related to B, we have B related to A, then that relation is symmetric. Example: less than or equal to on the set of natural numbers, on the full set of natural numbers. Do you think that it is a symmetric relation? What is your guess? I hope you guessed it right. It is not a symmetric relation. I am giving you a counter example. 1 is related to 2 because 1 is less than or equal to 2. But 2 is not related to 1 because 2 is not less than or equal to 1. So here we have a pair where A is related to B but B not related to A. One counter example is enough. Now look at equals relation on the set of natural numbers, which you can easily verify as an equivalence relation, as a symmetric relation. If 2 elements are equal, then they are equal both ways. That's it. I hope you are getting what a symmetric relation is. With that assumption, I am moving on to transitive relation. Look at the definition first. I think that is the easy way to convey that. A relation R is said to be transitive if whenever A related to B and B related to C, then A must be related to C. That is, if AB is in the relation and BC is in the relation, then transitively AC we are getting in the relation. You verify this given relation as a directed graph. 1 is related to 2 and 2 is related to 3. We must have 1 related to 3 which is there. So, that is okay. Now, we have 1 related to 3 and 3 related to 4. So, we must have 1 related to 4 which is also luckily there, and 2 related to 3 and 3 related to 4, we must have 2 related to 4, and that case also is present, and hence the given relation is transitive. Now, look at these relations less than or equal to on natural numbers. What do you think? Is it a transitive relation on the full set of natural numbers? Yes, it is, because whenever A related to A is less than or equal to B and B is less than or equal to C, then A must be less than or equal to C. Now, what about not equals on natural numbers? What is your guess? Can it be transitive? It is not. I am giving you a counter example. 1 is related to 2 because 1 not equal to 2. 2 not equal to 1 and hence 2 is also related to 1 because not equal to is the relation. Now, see, 1 is related to 2 and 2 is related to 1. So, if it is transitive, 1 must be related to 1. So, what is the relation here? It is not equal to. If 1 is related to 1 means 1 not equal to 1, but which is not true. So, here we are getting an example which is a counter example, and hence we proved that it is not a transitive relation. And what about equals on natural numbers? You can easily verify that it is a transitive relation. So, I hope you are getting what a transitive relation is, and now we have enough information for us to define an equivalence relation, which is defined as an as a binary relation which is reflexive, symmetric and transitive. If a binary relation is reflexive, symmetric and transitive, then that relation is called an equivalence relation, which is having some nice properties. Examples: on the set 1, 2, 3, given a relation R1, which you can prove as not an equivalence relation because it is not reflexive. If you can prove that it is not satisfying any of these 3, then that is enough. Now, we are proving that this is not reflexive because 2 is not related to 2. Okay, so cannot be equivalence. R2, we can prove that it is not symmetric because counter example is there, 1 3 is there, then 3 1 must be there, but it is not present. So, it is not symmetric. R3, you can verify it as an equivalence relation, and that verification is left as a homework exercise for the interest of time. You verify that it is reflexive, symmetric and transitive. And I am giving you another simple relation which also you can verify as an equivalence relation, which is actually the simplest equivalence relation on this set, because to be reflexive we need all these 3 pairs, and that 3 pairs becomes or forms an equivalence relation, which is the simplest equivalence relation on that set. And for that purpose, for any given set, you can have set of n pairs if n elements are there, forming an equivalence relation. So, I hope you are getting what an equivalence relation is. Now, let us look at an example real life situation where you can have an equivalence relation representing something. Here I am giving you a set of 12 students in our department of Computer Science and Engineering, and defining a relation as this. Two students S1 and S2 are related if they both are studying in the same semester. Say if they both are in the S7, then they are related. If they both are in S5, they are related. Two students are not related if one student is in one class and the other one is in a different class. Okay. The question is it an equivalence relation? What do you think? The answer is yes. You can prove that it is reflexive, because if you look at any student, that student is studying in a class. For example, Rajesh Awar is in the 7th semester, S7. Rajesh Awar is related to Rajesh Awar because both are the same student, and so they must be in the same class. Rajesh Awar is in the same class as that of Rajesh Awar is trivially true. So it is reflexive. It is also symmetric because if Rajesh Awar is in the same class as that of Nimisha S. Nair, then Nimisha S. Nair must be in the same class as that of Rajesh Awar. Because why is it that Nimisha S. Nair is related to Rajesh Awar? Because they both are studying in S7. Because of that fact, the other relation is also there. So it is easy to verify that it is symmetric. Similarly, we can extend it and say that it is transitive as well. See, Nimisha S. Nair and Rajesh Awar are related because they both are in S7. So which means Rajesh Awar is in S7. Now we are given that Rajesh Awar is related to Fasna Harris, meaning Fasna Harris is in the same class as that of Rajesh Awar, so again in S7. So now we are getting that both Nimisha S. Nair and Fasna Harris are in S7. So naturally they are also related. I hope you are getting it, otherwise think about it offline and verify that this relation is symmetric, reflexive and transitive, and hence an equivalence relation. And now we are going to look at what are equivalence classes. Every equivalence relation induces some subsets on this set. Now you look at the set of all pairs related here, and why double-ended arrows is because it is a symmetric relation. Now you can see that actually this forms three different subsets or disjoint subsets. And how will you collect it? You start from an element or from a student. You start from Nimisha S. Nair and you collect all the other students related to Nimisha S. Nair, right? Nimisha S. Nair is related to Rajesh Awar, and Rajesh Awar is related to Fasna Harris, and from transitivity Nimisha S. Nair is related to Fasna Harris. Similarly, it extends to Google LK also. So that is the first set. Starting from an element, you collect all those elements related to that particular element, and the element you started with can be taken as a representative element of that class. It can be any element, it does not matter, and you collect all those students related to that particular element. Even if you start with Fasna Harris, you will get the same set. They are in fact the students from this set studying in the 7th semester. Okay, now you are getting a subset which is not covering the entire set. So you start with the left out case. Maybe you now start with Adira and you collect all the other students related to Adira, traversing through this list. You will get another subset which is actually the set of students in the 3rd semester. Now you start with a left out case, maybe Paurnami Pradeep, you go and collect all the elements related to that particular element. You are getting in fact the students from this set who are in the S5. So here you can observe that the equivalence relation is actually forming some classes on the set. What is a class? It is a set of elements, they are pairwise related. You can easily prove it because it is transitive, symmetric and reflexive. Nimisha S. Nair is related to Nimisha S. Nair because it is reflexive, and Nimisha S. Nair is related to Rajesh O.R. Then Rajesh O.R. must be related to Nimisha S. Nair because it is symmetric. And see that Nimisha S. Nair is related to Rajesh O.R. and Rajesh O.R. is related to Fesna Harris. And then from transitivity, Nimisha S. Nair is related to Fesna Harris. And if you apply that transitivity, reflexivity and symmetric properties, you can see that they all are pairwise related within a set, within a class. And not two students in two classes are related because they are in two classes. And these are what are called equivalence classes. An equivalence relation subdivides or partition the given class, given set into a number of disjoint subset called equivalence classes. And the number of equivalence classes will depend on the relation that you are looking at. It can be one. For example, if you look at the natural numbers, and if you look at the following relation, two elements are related if both are natural numbers, and you can verify that it is an equivalence relation because every pair of elements are related. This is an equivalence relation, and if you look at it, you will get a single equivalence class where every natural numbers are coming. I am giving you an example, and I hope you are getting it. And moving on to the formal definition of equivalence classes, an equivalence relation partition a set into a number of disjoint subsets called equivalence classes. For example, here this is the equivalence class represented by Nimisha S. Nair. So the equivalence class represented by an element. If you take the union of all the equivalence classes, you will get the original set, and each equivalence class is disjoint when compared to a different equivalence class. And what is an equivalence class for AI? It is the set of all elements in A related to AI. And that's it. I hope you are getting it. And with this we are coming to the last part of the lecture, where I am giving you an exercise problem for you to practice and understand how can you verify that whether a given relation is an equivalence relation, and also if it is an equivalence relation, how can you find equivalence classes. Here you can see that it is an equivalence relation, and it is an interesting case because the set is an infinite set, and if you get it correctly, you can see that you are getting only 3 equivalence classes, and the 3 equivalence classes, when you take union, will give you back the set of all integers. So do it and see how it works. Today we have recollected some basic information about binary relations. We discussed about reflexive, symmetric and transitive relations. We have seen examples. Then we defined equivalence relation as a binary relation which is reflexive, symmetric and transitive. And we also saw that any equivalence relation on a set will partition or subdivide the original set into a number of disjoint subsets called equivalence classes, so that if you take the union of all the equivalence classes, you will get back the original set, and that is why it is called a partition of the given set into a number of disjoint subsets. In the next class we can see an interesting equivalence relation on the set of all strings over an alphabet set representing regular language. So, we shall discuss about Michael-Nerod relations. They are binary relations, equivalence relations on the set of strings. Thank you.